Fred Hoyle's Steady-State Universe Theory by Dave Marsland of Cardiff Theosophical Society. Fred Hoyle, 1915 to 2001, a prominent figure in astrophysics, proposed the steady-state universe theory in 1948 as an alternative to the Big Bang theory. This theory posits that the universe has no beginning or end and maintains a constant average density over time. Hoyle's steady-state universe was a significant departure from the prevailing cosmological model at the time and sparked extensive debate within the scientific community. To understand the significance of Fred Hoyle's steady-state universe theory, it is essential to consider the historical context in which it emerged. In the early 20th century, the prevailing view of the universe was based on the idea of a static, unchanging cosmos known as the steady-state model. This model, supported by scientists such as Albert Einstein, assumed that the universe had existed indefinitely without a beginning or an end. However, this view was challenged by the observations of astronomer Edwin Hubble, who discovered that distant galaxies were receding from us, indicating an expanding universe. The Big Bang theory, which emerged as a result of Hubble's observations, proposed that the universe began as an extremely hot and dense singularity approximately 13.8 billion years ago and has been expanding ever since. This model gained widespread acceptance within the scientific community and became the dominant cosmological framework. However, Fred Hoyle, along with his colleagues Thomas Gold and Hermann Bondi, sought to offer an alternative explanation for the observed phenomena, leading to the development of the steady-state universe theory. The steady-state universe theory is based on several key principles that distinguish it from the Big Bang theory. One of the central tenets of the steady-state universe is the concept of continuous creation, which proposes that new matter is continuously being formed to maintain a constant average density of the universe as it expands. According to this principle, the universe appears the same at all points in time, with no discernible beginning or end. Another fundamental aspect of the steady-state universe is the notion of the perfect cosmological principle, which asserts that the large-scale properties of the universe remain uniform over time. This principle implies that the distribution of matter in the universe is homogeneous and isotropic on a grand scale, with no preferred location or direction. Fred Hoyle and his colleagues presented several pieces of evidence in support of the steady-state universe theory. One of the primary arguments in favour of the steady-state model was the observed redshift of distant galaxies, which was traditionally interpreted as evidence for the expansion of the universe in the context of the Big Bang theory. However, Hoyle proposed an alternative explanation for the redshift, known as the tired light hypothesis, which suggested that the redshift was caused by the interaction of light with intergalactic matter as it travelled through space, rather than the Doppler effect resulting from the expansion of the universe. Furthermore, the discovery of quasars, which are extremely bright and distant celestial objects, was initially interpreted as supporting evidence for the steady-state universe. Hoyle and his colleagues argued that these objects could be the site of ongoing matter creation, consistent with the continuous creation aspect of their theory. Despite the initial appeal of the steady-state universe theory, it faced significant criticisms and challenges from the scientific community. One of the most notable objections to the theory came from the growing body of observational evidence supporting the Big Bang model, including the discovery of the cosmic microwave background radiation, which is considered a remnant of the early hot and dense phase of the universe. Additionally, the steady-state model struggled to account for the evolution of galaxies and the changing abundance of chemical elements in the universe, which the Big Bang theory could explain more effectively. The concept of continuous creation also faced theoretical challenges, as it required the introduction of new physical processes that were not supported by existing knowledge of astrophysics. Despite its eventual decline in favour with the scientific community, Fred Hoyle's steady-state universe theory has had a lasting impact on the field of cosmology. The debates and discussions surrounding the steady-state model contributed to a deeper understanding of the evidence for the Big Bang theory, leading to refinements and enhancements in our understanding of the early universe and its subsequent evolution. Furthermore, the intellectual rigour and creativity displayed in the development of the steady-state universe theory served as a testament to the importance of considering alternative hypotheses and challenging prevailing paradigms in scientific enquiry. The legacy of the steady-state model lies in its role as a catalyst for further exploration and refinement of cosmological theories, ultimately contributing to the rich tapestry of ideas that continue to shape our understanding of the universe. Fred Hoyle's steady-state universe theory represented a bold and innovative attempt to provide an alternative cosmological framework in the face of the growing acceptance of the Big Bang theory. While the steady-state model ultimately faced significant challenges and criticisms, its historical significance and impact on the development of cosmology cannot be underestimated. The theory's emphasis on continuous creation and the perfect cosmological principle stimulated valuable discussions and investigations that have enriched our understanding of the universe's origin and evolution. As we continue to probe the mysteries of the cosmos, the legacy of the steady-state universe theory serves as a reminder of the dynamic and evolving nature of scientific enquiry.